Good evening, everyone. It is like 4:30 on a Monday, and we're talking about Chapter 3. Chapter 3 includes recursion, search algorithms, and algorithm analysis. Exciting stuff. So, first thing we're going to talk about is recursion. Uh, a recursive algorithm, to start off, solves a problem by breaking it into smaller subproblems. You can think of your homework maybe as a recursive algorithm because you have to do, section 1A, 1B, 1C, and so on and so forth. If you want a real world example, if you have to mow the lawn, let's say house, lawn, you should probably mow, the front half and then the back half, and then you can even split that up. So a recursive algorithm just looks to break these problems up into smaller subproblems. One thing that you can do with functions is call the exact same function. In a couple of our programs, we've seen, I know that maybe these functions get called by other functions. So function 1 may call function 2 at some point inside of it. What we can also do is call function 1 within function 1, and this is a recursive function. On the screen, we have message. What it does is it prints out, this is a recursive function, and then it calls message again. One thing to keep in mind with recursion is the need for a base case. The base case is essentially just the solution that we're looking for, or just something to bottom out and stop the recursion. A recursive algorithm has a base case which returns a value without recursion. This is where the function is done. So with this diagram, we start whatever function we're working on. We check whether the base case is true or not. If it's not, we call the same function again, and we go through the loop. If it's true, we return the data, and we end the function. Which brings me back to our example. We have our message function once again, and it's going to keep calling itself. That's kind of an issue because it'll do it forever. So I have a slightly different version of it up on screen, and if I compile it and run it, was that message.cpp, it will do this forever. So, rats make me crazy, a rubber room with rats, and it will just keep on going. Oop, that's not what I wanted. So, it does not have a stopping point. So how do we change that? Well, we give it a base case. So we change it a little bit. We're passing in an integer called times, and it's going to determine how many times we run this function. So if we look at messagefix.cpp, in our main, we call message 3 times, so it will print this 3 times. So we come in with times is equal to 3, so times is equal to 3. First call, we print everything because times is greater than 0. And then we call message again. This time, times is equal to 2, print everything, times is equal to 1, print everything, and then on the final one, times is equal to 0. Whenever it's equal to 0, we do nothing since it's a void function, and we kick out. So let's run message fixed. You notice we only print it 3 times, so crazy, I was crazy once, they locked me in a rubber room, and we can see it 3 times. So this is one of the biggest things with recursive functions, is you need to be sure to add a base case. I think that gets hammered in through these slides and just through the general chapter, because it's the most important part. So we have a sort of a graph or a flow chart on messagefix.cpp. And so up here, we call the message function from main. So message of 3. So value of times is 3. We print everything, and we call message with 2. Print, and we call message of 1. Print, message of 0. And then down here we say, oh, base case has been achieved. And we start going back. And so each one of these functions hits the end, we run out of code to run, and so we return to the function that called us. So each time the function is called, a new instance of the times parameter is created in memory. So your memory is a data structure that we haven't learned yet. It's a stack. And so at the very first time we call it, we put times of 3 down. We call message however many times, and every time we add a new times into memory, or a new variable into memory. Once we finish the top one, so 0 times, we'll take it off the stack out of memory. Then the new top of our stack is times at 1. So finish with that function call, we take it off. Finish with this function call, we take it out. And then we finish with this one and we take it out. So whenever you recurse in memory, we are consistently adding stuff to memory. We are consistently adding more and more and needing more resources. So recursion is good in a couple of situations. If you can break your problem down, that's fantastic. This also kind of factors into the dry principle, because if you're trying to solve something over and over again, why do it by hand when you can call a function? The other cool thing with recursion is you never have to use it. You will never be required to use it, outside of class problems and practice, stuff like that. But outside of that, you do not have to touch it. This brings us to the good, the bad, and the ugly of recursion. The bad, it's not efficient. Every time you make that function call, your compiler and your computer have to set up a new function call, do all of this overhead, and it adds up. The good part is recursion can solve easy code very easily, and it's compact. The ugly part of it is recursion itself. Recursion itself is a skill, and you have to learn how to think recursively. Some people have the knack at it, and others take more practice and more problems to do it. So the basics of recursion, you have a base case and a recursion case. If it can be solved without the recursion, then we stop. If it can't, then we need to recurse and keep going. Going back to the lawnmower example, if I have this big old patch of land, and I'm sitting here going near, and I hit the end of a strip, well, the lawn's not mowed yet, so I probably have to turn it around, keep going, and every time I'm saying, am I done yet? Am I done yet? Then finally, once we hit the bottom, oh my gosh, we have no more yard to mow. We're done. So there's a couple of in-class practices. If you want to pause it and, sit there and scribble on a piece of paper and figure out what it is or what it's doing, you're more than welcome. I'll give you a couple seconds to do that. But taking a look at this function, our call in main, we are calling function at 10. Then looking at the value of the function, or what the actual function does, we are going to print whatever number we're at, check if it's less than or equal to 0, so that's our base case. If it's not, we call the function again. So give you 5 seconds to pause, and then I'm going to run through it. So we are passing 10 in. Actually need a workspace. Give me 1 second. Okay. So we have our base function, so func of 10. this is where we are starting. On the left, I'm going to do printing to the screen, and here I'm going to keep track of the recursion. So recursion. So at the very beginning of our function, we are going to print whatever number we're at. So at the very top, we're going to print 10, and 10 is greater than 0, so we're going to recurse. So we are going to call function of 10 minus 1. You can simplify that to 9 if you want. And then whenever we return, we're going to add 10 to it, because it's what? Return function 10 minus 1, return whatever the num minus 1 plus num. So now we enter into the second recursion. So our number is 9. 9 is greater than 0. And we get func of 9 minus 1 plus 9. So I'm going to skip ahead a couple because this pattern is going to follow all the same. We're going to get 8 minus 1 plus 8, 7 minus 1 plus 7, repeat until we get down to 1 minus 1 plus 1. So on the left, we're still just printing, so 8, 7, 6, 5, ... 1. So whenever we get down here, where we are passing in 0, we're going to check if 0 is less than or equal to 0. Since it is, we're going to return nothing. Return 0. So now we get to sort of unravel all of the work we've done. So we're going to take that 0 and replace it here, where we made our function call with 0. So that evaluates to 0 plus 1. So we're going to return 1. So that was at 1. For the next one, we're going to return 1 plus 2. For the third one, we're going to return 3 plus 3. For the fourth one, we are going to return 7 plus 4, 11 plus 5, 16 plus 6, 22 plus 7, 28 plus 8, 36 plus 9, 45 plus 10. So we should end with 55, assuming my math is right. So let's go ahead and get that code cracked open. That is Recursion Practice 1. Recursion Practice 1. And run it. 55. So we are correct. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then the most important part is remembering to substitute whatever value is returned from that function. And it's always going to return upwards in the direction that we added the calls. So what do we get from this? We get 55. Put in a smiley face because I added correctly. The rest of the recursions that we're looking at are a lot easier to wrap your head around, or at least in my opinion they are. So with this one, we are passing in 5. We're going to check if the number passed in is greater than 0, which 5 is. And then we're going to loop from 0 to 4, since we're not including 5. So this loop is going to run 5 times, first time. And we're just going to print stars. So first run is going to be star, 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 and star. And we call function with 4. So next time we run it, it'll go 1, 2, 3, 4. Next time will be 1, 2, 3, 1, 2, and then 1. At this call, we are adding function of 0 to the stack. We check, is num greater than 0 or is 0 greater than 0? It is not, so we stop. Gonna go ahead and compile and run that one for you. And we get 5 stars, 4 stars, 3 stars, 2 stars, and 1 star. So, high five if you got it right. If you got it wrong, still give yourself a high five, you tried. So, looking at this one kind of builds into making sure you return your functions in the right way. So we are passing in a string, a 0, and the size of the string. The 0 is a position, and size is the size of the string. We're going to check whether or not we have hit the end of the string. And if we haven't, we are adding another call to the stack with position plus 1. So going back over to my workbook. So we are calling function with the string hello, 0, and I'm going to say 5. I could be wrong, but... So we are going to check whether or not we've hit the end of the string. So is 0 greater than 5? It's not. So I'm going to write stack on here. So this is our original call. I'm going to tab over to show that this one will come next. Same string, 1, 5. So 1 is not greater than 5, so we do it again. 2, 5. Then we're going to have 3, 5, 4, 5, and then 5, 5. So whenever we hit this point, where position is... Oh, one more, I lied. 6, 5. So once we hit the point where position is greater than the size of our string, we know we're at the end of the string. So now we can end this function, so nothing will happen here, as the work is inside this if statement. So this call just disappears, nothing happens. So scribble that out. And it's gone. Now we have to start resolving our calls, now that we've hit the base case. So this one is going to print our string at position, whatever. So we're going to cout string at 5. This function will end, so we can scribble it out. We print out string at 4, so str 4. String at 3, string 2, and then string 1. So what does this end up giving us? Printing the string in reverse. So output will be OLLEH. I hope that helps kind of showing the order that we have to resolve these functions in, because it's always going to be we have to resolve the last added function first and then work our way back up. So I think this is the trickiest function outside, or the trickiest practice function. So we are taking sign, we're asking, hey, do you need a hug? And then we are calling sign, but we are pre-decrementing. So assuming the user enters 5, we call sine of 5. So the thing with this function is because it is a pre-decrement instead of a post-decrement, so it's the difference of x plus plus or plus plus x, maybe minus minus, either way, is when it comes before x, we increment or decrement the number before we do anything with it. So what this is saying is see out whatever. We are saying n minus equals 1, or n is equal to n minus 1, and then we are calling sine with our new n. If it was the other way and the minus signs were after n, it would be equivalent of saying sine, close enough, of n, and then n minus minus. If we do it that way, it will be infinite because we will always be passing 5 into sine. So for the output is on the next slide. It outputs the sign 5 times. So we have, this is 5. We do minus minus n with our call. 4 gets passed in, minus minus n, 3, 2, 1, 0. Whenever it's 0, we don't do anything in this case, and then we just go back and we print. Or we just return up the calls. So, if you haven't done it, or if you're just watching this video now, we have a in-class practice. I believe it's still open. I think it has a due date, but the due date doesn't mean anything. You're just writing a function that will recursively calculate the sum of all numbers in the array. The function will have to accept the array as one of its parameters, and you just have to show this off. So, what are the uses of recursion? Can we actually see some? Of course you can. So, one use of recursion is finding the greatest common divisor for two numbers. Looking at GCD, that's just trying to find what number multiplies into both of them, but it's the biggest number. So if we have the numbers 2 and 4, we can break it up into 2 times 1 is equal to 2, and then 2 times 2 is equal to 4. So that is what the greatest common denominator is. Euclid's algorithm says the GCD of two positive integers, x and y, is either it divides evenly, or we have to pass in y for our new x, and then whatever the remainder, so I'm going to say modulus xy. And looking at recursion practice 6, oh, I almost forgot, my bad. So if we look at recursion practice 5, it does have the solution for the in-class practice if you were stuck. So we pass in the array and the position that we are currently at. And then we just have to return the recursive function call with position plus 1 and the array at that position. So there you go. Looking at recursion practice 6, this is the greatest common denominator program. We enter two numbers, num1 and num2, and we are either returning the modulus or... I lied, let me rephrase that. So if x divided by y, if it is an even no remainder divide, we return y. If it's not, we swap them and add the remainder. So let me actually get an example of that before I start running my mouth. So if we have, I'm going to say 50 and 3 as our numbers. So 50 divided by 3, that is 49 remainder 1. So it's not even. Is it 49? 30? It's 48 remainder 2, my bad. So 48 remainder of 2. So we have to swap these. So it'll be 3, and whatever the remainder of 53. So I'm actually going to swap these real quick. One sec. No. I don't know what I'm doing. It's a Monday. So we're going to pass in 3, and then 3 modulus 50. So if the number is bigger, I want to double check this real quick. 3 modulus 50. We get 3. Okay, maybe this is a horrible example. So what we're going to do instead is run this program so I can find out what this is. Recursion practice 6.cpp, 3 and 50. The greatest common divisor of 3 and 50 is 1. So there's nothing that multiplies into 3 to get us 50. So probably a bad example. Let me run it again and do 6 and 50. The greatest common divisor of 6 and 50 is 2. So this does work with math. If we go back and we add in a print statement that just goes, hey, this is x and this is y, we can track what's happening. So recompile. Let me do some fun numbers. 123 and 999. So the first call, we get 999 and 123. Those don't go together, so we swap, do the modulus on the right side. We have 123 and 15. Those don't divide, swap, modulus. We have 15 and 3, and then finally we get 3 out of it. So the greatest common divisor of 123 and 999 is 3. I think this is a really cool concept. Fibonacci numbers. This is just great recursion examples. So the rules for Fibonacci numbers, outside of the first two, is that you take the previous number. So in this one's case, we're going to take 1 and 1, and we get 2. For the next number, we take 2 and 1, 3 and 2, 5 and 3, and you can see the pattern that goes on. So we have recursion practice 7. If I can pull it up. And this is just saying the first 300 Fibonacci numbers. And looking at the code for it, if n is less than or equal to 0, we return 0, or if it's equal to 1, we return 1, because these first two numbers kind of have their own rule. Outside of that, we are taking the previous number and the current number. So G++, recursion practice 7, and we run it, and right now it is just doing math. Just a whole bunch of math. So if we want to give it just a minute. Maybe a little more than a minute. So I'll run through what the code is doing. So for every number between 0 and 300, it is calling a fib of whatever that number is. So we know the first two are base cases, so it'll return 0 and 1, and then whenever we hit this Fibonacci number, not this Fibonacci number, the next one, so this number 2, it's going to call fib of 2, which then calls fib of 0 and fib of 1. So every number is calling at very minimum two other Fibonacci numbers. If we go to a more complex one, like a Fibonacci of 10, it's going to have to call fib of 9 and fib of 8, 9 and 8. So 9 is going to call 8 and 7. 8 is going to call 7 and 6. 7, 6, 6, 5. So the reason it's taking absolutely too long is because we're doing a whole lot of recursive calls. Let me check. Oh, my CPU is very unhappy right now. So I'm gonna go ahead and cancel this and give us a more realistic number to work with. Let's say 50. Maybe. I'm just gonna do 10. Okay, so we get 0, 1, 1, 2, 3, 5, 8, 13, 21, and 34. I'm gonna slowly pump this up and see how high we can go. 25 is fine. Let's try 50. And 50 is where it starts hating itself. I mean, that is a whole lot of math. So I'm going to let that run in the background just to see if it does. So recursion is useful. You can use it for Fibonacci numbers, the greatest common divisor, and you just have to find these subproblems that we can fix. I think this is a really great YouTube video. You can watch it or don't, but if you need a second opinion or a second explanation on recursion, I think it's great. Now we go to search algorithms. So search algorithms they're more or less just trying to find a needle in a haystack. Search problem is finding a specific value, usually called a key, in a collection of data. This collection can be a linked list, an array, just some sort of data. So on screen, we are trying to find the number 20. We are going to check the array at 0, 1, 2, 3, 4, 5, and 6 until we find it at array of 6. Here are a couple of search algorithms. The one we're going to talk about today are linear search and binary search. And these two more or less make up the core of a lot of what we're going to talk about in class. So, yippee. What is a linear search algorithm? A linear search algorithm is a sort of brute force algorithm in which we just step through all of the array and check, is this number equal to what I'm searching for? And then we end if we find it or if it's not in the array. So two different ways to look at this. We have linked list and arrays, in which we're just going to step, 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 all while checking. Hey, is this equal to what we're looking for? Within the arrays, we're going to, hey, is A equal to FF? Nope. So we step. Is BF equal to FF? Nope. And we step. And we just keep on going until we find it. So here's a little GIF of how it works. It just steps along until it finds the number, and then it stops. And if it doesn't find it, it keeps on going until it ends. I think this is a really great link. Algorithm Visualizations, a guy who's a lot smarter than me, built this tool. I think it's Control-click. Nope. So we have a list of 31 elements, and we are searching for nothing right now. Oops, got to input it. So if I'm looking for, let's say, 119, maybe. Maybe. Am I just stupid? There we go. Numpad doesn't work. I'm so sorry about that. So if we are looking for 153 with a linear search, it's going to step through until it can find that number. And it finds it here and returns the result. If we're looking for a number that's not in the list, so linear search of 1, it's going to keep stepping through this list. One other thing is that since this list is sorted from minimum to maximum, if the number it finds is greater than the number we're looking for, it just stops. So if I look for 1000, it's going to sit here and step through over and over and over again until it hits 31. Okay, maybe not that fast. It's going to keep on going until it hits the end of the array and it doesn't find anything. So I'm going to show these in class, but if you want to stop, open the slide and go watch this, you're more than welcome to. I remember watching this when I was in your position, and I laughed. Linearsearch.cpp is the example we will be looking at. Oh my gosh. The Fibonacci numbers worked, and we hit integer overflow. That's always fun. So, looking at it, we have an array, 87, 75, 98, 182. We look for 100. We pass in the array and the size of the array. And then either we don't find it, or we find it. So, we have an index, a position, and whether or not we have found the number. We are going to say, hey, if we haven't found the number yet, and the index is still within the size, check the value, and then keep going. If we do find it, we kick out of the while loop, and we return position. So, G++, gotta go off one, linear search, and run it. So on test 4, 0, 1, 2, 3, and then we add 1 to get it 1 based. We earned 100 points. We change this to 99, compile and run. We will return false, and we didn't find anything. So, linear search, it is super simple to understand. Like, if I can understand it, you all can understand it. It doesn't require data to be stored in any order because we're just going to go through and look anyways. And it's space efficient. We just need the array to go and check. It's super slow. Super slow. If you have huge amounts of items, it's going to take so long to check them all. So, with algorithms, we have a couple of different ideas to go with it. We have like a best case scenario, average case, and a worst case efficiency. So on the average case, we're going to find the number, if it exists, in n divided by 2 comparisons. So on average, there's a chance it could be at the first half of the list, and there's a chance it could be at the second half in the list. For the maximum, like the worst case scenario, it's not in the list at all, and we have to check the entire list. We can also look at the runtime of a linear search algorithm. This is the sort of other metric that we use to check algorithms. And we can say, hey, if it takes us 1 second to run through 1 million elements, and it takes 10 seconds to run 10 million elements, this is a very linear, where'd my pen go? A linear growth. So if we were to plot it out, it would just be a straight line all the way. But because it's a straight line, once we get to giant numbers like 200 million or 353 million, it's going to take so long to finish, and that's not realistic. If you were on Amazon looking for products, if you were on Google looking for whatever you all Google nowadays, if something takes 5 minutes to run, I don't care about that subject. I'm not looking anymore. So next we can get into a binary search algorithm. It does the exact same thing, or results wise, of just looking for a number, but it does it in a different way. So instead of going from the beginning to end, we look at the halfway point in the number. If that number contains the value, then we're done. If it doesn't, if the number is less than whatever we're looking at, we split the list in half and we search the remaining half. If it's greater, we split and check. And then we just repeat that process. So if we're playing a guessing game and friend guessed, let's say 31, well, we're going to ask 50. They're going to say, hey, is my guess higher or lower than 50? They're going to respond less than 50. So we know we can cut everything above 50 out. Next, we ask 25. They're going to say, oh, 31 is greater than 25. We cut that half the list out, and we just keep going until we guess the number. That took 4 guesses versus doing linear search that would have taken 31. So, animation for binary search, we're looking for 47. 14 is less than 47, so we know we only have to look above 14. 45 is less than 47, so we look above it, and we hit our number. So, another flamenco dance demonstrating searching algorithms. And we have a couple of examples code-wise. So we have with recursion and without recursion. So without recursion, what we're going to do is call binary search, looking for a number, and then whether or not it has it. So we're doing a while loop just like the linear search, and we're saying, hey, if we haven't found the number yet, and the first of the array of our subsection is less than the last index of our subsection, we can keep going. And we calculate the middle point. We check if the middle point exists, or if it's the value we're looking for. And if it isn't, we have to scoot. Now, the way we scoot is we set... I'm grabbing my pen, hold on. So we have our array. Let's say our number is like right here. So we're going to check the halfway point. And we say, hey, is the number greater or less than or greater than, what we're looking for? In this case, it would be greater than, whichever, I'm losing it. So we have our first of our array. This is going to be index 0. Let's say this one is last, and we're just going to say 10. So everything before this, middle would be 5. It'd be 4, I lied. So middle would be 4. So what we're going to do on the next iteration, we're going to set first equal to middle, and last will stay the same. If it's the other way around, we would set first, same as always, and we set last equal to middle. So either way, we are shifting in one direction or the other. We get a new middle. So we're changing our search window. So we either set last equal to middle minus 1, or first is equal to middle plus 1. So go ahead and run that. So binary search without recursion. I want to search for 151. So that number does not exist in the array. If I try it again and do 142, that ID is found in element 2. Wish it gave us the step number it took to calculate that, but it doesn't. So now, here's a recursive version of it, in which we return the middle, or we return whatever the next call would be. So let me pull that up. So if we find it, we return middle, and if we don't, we add another binary search call to the stack. So binary, let's say 1, 10, and our value would be 5. So let me not do the center of it. That's probably better. Let's do 3. So what we're going to do is we're going to check 5. 5 is not the value we're looking for. So we're going to do another call of binary 1, 5, and 3. The middle between 1 and 5 is 3. So we say, hey, found it. Then we return 3 up to this one. This one returns 3. So you can do it recursive, or you can do it normally. Binary search, it's easy to understand, it's time efficient, it's space efficient. The only issue is you have to sort your data. If it's unsorted, binary search will not work. So looking at the comparison, we looked at linear search, now we have to look at binary search. The maximum amount of comparisons with binary search is log 2n. So powers of 2 are used because we are only checking half of the array at any given time. And we have to find the smallest power of 2 that is greater than or equal to the number of arrays in the elements. So if we have 50,000 elements, we have to find whatever is going to be greater than that. So if we have 2 to the 16, I lost my cursor, there it is. If we have 2 to the 16, that is greater than 50,000, which means at the very max, we are going to make 16 comparisons. If we had linear search, at the max would be 50,000 comparisons. And then finally, we can analyze, that's the word I'm looking for, some of these algorithms. So a couple terms that we're going to be talking about is efficiency and growth rate. Efficiency is just how well this algorithm will run, and growth rate is, hey, if we have more numbers, how much slower will it run? We have big O notation to tell us this. That's a mathematical way to describe the efficiency of a class, or the efficiency class of an algorithm. If you will remember back to algebra, I want to say, we had x squared, x cubed. Big O notation follows the same sort of thing, polynomials, or logarithmics. So if an algorithm is big O of n, it means that the running time is proportional to the number of elements. If it was n squared, we're going to need whatever that quadratic number would be amount to find. So a couple other notations in algorithm analysis. You really won't see omega and theta at this point. We talked about it in whenever I took algorithms, is 6400, I think. So the main thing that we're going to be looking at is just big O notation. This is, hey, at the very worst, in the most horrible spot, this is how the algorithm will run. But omega is the best the algorithm can run, and theta is the average case. So how do we calculate what big O notation is for an algorithm? We have to add the best case, the worst case, and the average case. So we have the linear search algorithm, and we're going to say, hey, best case, it's the first element. Worst case, it's the last element. And on average, it's going to be n divided by 2. Now, if you'll notice, this doesn't come out to some pretty number. You have to think of it in terms of n. So with algorithms, whatever your highest power is, that's usually what it's going to be. So if linear time had a worst case of n squared, and then everything else was like n and some sort of constant, this n squared is going to outpace any other number, so we don't have to worry about the other numbers. So if we take, n and n squared, n will be 1, 2, 4, 3, 9, 4, 16, 5, 25. N squared is already 5 times the size of n. So the higher exponents will always grow faster, and so we have to consider them for our time. Algorithms that are in big O n squared are said to run in quadratic time. An example is bubble sort. We'll learn that a different day. There's also logarithmic time. Algorithms that run in big O of log n are logarithmic time. Example is binary search. So it's whatever log of n, I think it's rounded up. So the ceiling of that's how many comparisons we'll have to make. Finally, we have exponential time. If you have an algorithm in exponential time, I'm sorry, it will never get done. An example of it is if we wanted to take every possible, I need to stop touching stuff. Every possible n letter combination. So if we had every 1 letter combination, that's just going to be the alphabet. D, E, F. If we had every 2 combination, it would be A, B, A, C, and so on. So these are very explosive in their runtime. 26 to the first power is 26. 26 squared, I don't know off the top of my head, but it's big. Pull up a calculator. 676 different options. If we do 26 cubed, we're at 18,000. So exponential time is very bad. If you do want to find big O of just random code, the most important part to look for are for loops. So if you can see under all of these different boxes and stuff, we are looping from 0 to n in this for loop, which means we'll touch every number at least once. So since we run this for loop once, we're going to have a big O of n. If we had nested for loops, went from 1 to n, or 0 to n, and then 0 to n again, it would be an n squared time. So this for loop, called that for loop. So realistically, it just depends on how many loops you're doing over your data. Because if we look down here at the code, or at the solution, so we have 1 operation, we will do this for loop once, and then we do all of this inside stuff some amount of time. So we get big O of n from that. The last 2 slides are just graphs sort of showing, hey, this is where it falls on the big O complexity chart. So linear search, we have a O of 1 best runtime, which is perfect. Cannot get better. With the average runtime, we are at O of n, which as you can see, it's pretty good. And then worst case of a big O of n. For our binary search and our big O notation, all of them are fantastic. It's all sitting at the best it can be. Best whenever the item is in the very middle, and worst case is log n plus 1 comparisons. So big O binary search is fantastic. That's everything. Sorry today was kind of all over the place, but hope you learned something. Take it easy, y'all.